Hello, my name is Lydia, and our team will be presenting ibuprofen's original versus green synthesis. So we're going to be going through ibuprofen's structure and biological mechanisms, and also some terminology like what is green chemistry and atom economy. And then we're going to be looking at the synthesis, so classical and the green synthesis, and specifically look at its mechanism and efficiency data. And then we'll arrive at the paper's conclusion and go through mechanism and go through references. So ibuprofen relieves pain, and it consists of an aromatic and carboxylic acid functional group. Its IUPAC name is 2,4-isobutylphenylpropanoic acid. And since we have a chiral center over here, because it's sp3 hybridized and we have 4 different groups attached, the S configuration is commonly used. The R configuration isn't that very pharmaceutically useful. So that's its structure. Ibuprofen works by competitive inhibition. So basically what we have here is a normal substrate that goes ahead, binds to an enzyme, and maybe it synthesizes some hormones. But in the case of a competitive inhibition, it binds to the enzyme and it prevents the normal substrate from being able to go ahead and bind. So it prevents the hormone from being synthesized. So in this case, ibuprofen is an inhibitor of COX-1 and 2. Which catalyzes the synthesis of prostaglandin. So that's what these enzymes catalyze. And prostaglandin is what causes inflammation. So by ibuprofen binding to the COX-1 and 2 inhibitor, it prevents prostaglandin from being synthesized and thus prevents inflammation, since prostaglandin causes inflammation. So green chemistry is a practice of synthesizing chemicals in a way that encompasses the following aspects. So it's sustainable, it's safe, non-polluting, and consumes a minimum amount of materials and energy, and produces little or no waste material. Atom economy is a way that chemists can evaluate the efficiency of a synthesis quantitatively. So higher atom economy means a more efficient reaction because less byproduct is produced. And below is the equation for it. So this means that if the numerator is larger, then that means that more of the atoms from the reagents go into making the product. So that is why a higher atom economy is more efficient. Okay, Doug.
Classical synthesis. So this is a mechanism for the classical synthesis. It consists of 6 steps, and this is the overview of the steps.
Okay, so the first step is a Friedel-Crafts acylation. So basically what we have here is this acyl group that goes ahead and adds para to the hydrocarbon substituent, which is electron donating. So it can either add to ortho or para, but we have steric hindrance, so we will choose the para position. The next step is a Darzens reaction. So first of all, we get the formation of an enolate, which is a good nucleophile. So then that's going to do a nucleophilic attack on the electrophilic carbon that is in the carbonyl. And then we get the formation of epoxide, where this electronegative this oxygen, negatively charged, goes ahead and does a nucleophilic attack on this carbon, bumps off the chlorine, which is a leaving group. Then we get the formation of this epoxide. Next up is an acid catalyzed ester hydrolysis. So this is a proton transfer, and we don't have enough time to go through the mechanism of ester hydrolysis. But basically what happens is this OET gets replaced with an OH. And then what happens is we get this little reaction going on where a base can go ahead, abstract this proton, and then we get the formation of a double bond, and then we get formation of another double bond here, which is what is shown over here. And then we get an epoxide ring opening, which is where we get this OH from. But what you'll notice here is that we form a enol, so then that can undergo keto-enol tautomerization to form this keto.
So the next step is when hydroxylamine attacks the carbonyl center and bumping the electrons onto the oxygen. Then a base obstructs or extracts the hydrogen, and the bond moves onto nitrogen, and the lone pairs from. So since we want to create a good living group, we do a couple of hydrogen transfers onto the oxygen and generate a good living group. The lone pair from nitrogen then comes down, knocking off the H2O, making it leave and generating an aldoxane. The next step is the dehydration of the aldoxane, and it starts with the lone pairs on oxygen attacking the carbonyl center of the acidic anhydride, bumping the electron onto the oxygen. And since we want to create a good living group for one OAC group to leave, we first start by a base subtracting the hydrogen and the bond collapsing onto the oxygen. Then the lone pair on the negative oxygen moves down, in turn kicking off the first OAC group. So after that step, we realize we have one more OAC group bonded to the nitrogen, and since we want to get a C triple bond and a base comes in, extracts the hydrogen, the bond moves to the C N bond and the OAC leaves, giving us our nitrile. The last step of the classical synthesis is acid catalyzed nitrile breakdown. So with this, since it's acid catalyzed, the first step is the proton transfer to the nitrogen, giving us a positive center capable, making water capable of attacking, doing a nucleophilic attack. And since we also want to create a good living group, that is the nitrogen, to make it a good living group for it to live, in order for us to get a carboxylic acid, we do a couple of proton transfers. And once we have just one H connected to the oxygen, water attacks once again, and another proton transfer is done in order to get an NH3, which is positive, and the lone pairs from oxygen can now come down, bumping off the NH3 plus to form NH3 in solution. And since we have H bonded to the oxygen, we can now let the ammonia in solution come extract that hydrogen, and the bond collapse onto the oxygen, giving us a neutral species. So the atom economy for the entire synthesis is 40.04%. And this is how they had that number, or that percentage. So since we earlier explained atom economy to be some sort of efficient way of finding what you desire from the total steps or the total reagent you use, we used the relative mass of the desired product, which is ibuprofen in our case. And ibuprofen has a molar mass of 206, and the total mass of the relative mass of total reagents, which is the mass of ibuprofen plus the total mass of every byproduct or waste generated. That gave us a total of 514.5. We did the math and we had 40.04. According to the green synthesis chemistry, 40.04 is a pretty inefficient percentage to get, and that is because this process involves 6 steps and 13 intermediate reagents, and these intermediate reagents or byproducts tend to be harmful to both human beings and the environment. HCl is an irritative compound. Ammonia is pretty poisonous and has adverse effects on aquatic ecosystems, and aluminum trichloride hydrate is also a poisonous substance or chemical.
So then we get green synthesis to the rescue.
The green synthesis was an improvement of the classical synthesis. The green synthesis is carried out in 3 steps, and here is the overview. Let's get to the mechanism in details. For step 1, the Fiedel-Crafts isolation, it involves isobutyl benzene and acidic anhydride. The reaction begins with protonation of the acidic anhydride to make a good electrophile. The isobutyl benzene acts as a nucleophile to attack the acidic anhydride. The electrons on the oxygen comes down and then bump off the leaving group. Deprotonation occurs to get back the aromaticity of the benzene, which forms isobutyl acetophenone. Acetic acid is the byproduct for this step. Let's move to step 2. Is the reduction reaction. This is a palladium catalyzed hydrogenation of aromatic ketone to alcohol. There is an activation of H2 by surface adsorption, which is facilitated by the palladium catalyst. The ketone adsorbs the palladium surface. The closeness of the ketone to the H2 surface facilitates hydrogenation, which gives the product 1,4-isobutyl phenyl ethanol. No waste is generated in this step. Let's move to step 3. For step 3, it is a carbonylation reaction, and it is also a palladium catalyzed reaction. The alcohol is in equilibrium with the benzyl chloride analog in the presence of excess HCl. This catalytic cycle starts with oxidative addition of benzyl chloride to the palladium center. Carbon monoxide is also introduced into the palladium center sigma bond. The final step is a nucleophilic attack of the acyl intermediate by water. The results in the release of ibuprofen, and the catalyst is regenerated. There is also no waste generated in this step. the efficiency data. The atom economy for the entire synthesis is 77.4%. And since this calculation has been done earlier, I will not go deep into it. The desired product is the ibuprofen, which is 206, and the 266 is from the waste plus the desired product, giving us a percentage of the 77.4%. Now, to the byproduct analysis. Acetic acid is the only byproduct produced from this reaction. All solvents and catalysts are reused and recovered. There is a minimum amount of waste created. From the earlier analysis of classical and green synthesis, the paper concludes that green synthesis is more efficient. It is because it is non-polluting and environmentally safe, which is less toxic, which means less toxic products are formed. It is efficient, that is higher percentage yield with fewer steps compared to classical synthesis. There is high atom economy because the green synthesis produces 77.4% and the classical synthesis produces 40.0%. Most reagents of the green synthesis are found in the desired product. This is why there is a high yield. Less intermediate resulting in more product yield because there is a lower chance of losing intermediates after each step of isolation. Compared to classical synthesis, the energy consumption is low. The green synthesis is an effective and efficient way out to an existing problem in a mass pharmaceutical synthesis. The process is environmentally friendly and a waste minimizing technology due to its virtually complete atom utilization. All the points mentioned above is a demonstration of the effectiveness and efficiency of the green synthesis. Below is the reference slide. Thank you.
Stop recording.